Good morning to all. Today we are going to discuss about stresses due to various types of loads. So last class we discussed what is strain energy or resilience. So the magnitude of the stress produced in a member due to the load depends upon the manner in which the load is applied. So as you know, different types of loads may be act on a member. The loads may be static or dynamic. So generally the dynamic loads depending upon whether they are constant or vary with the time. So let us see first of all what is static load. So a static load is a load which is applied slowly. Which is applied slowly means that is gradually applied. For example, I am considering 50 kilonewton loads. The load may be applied initially 0 and next 5 kilonewtons, 10 kilonewtons up to 50 kilonewtons. That is nothing but gradually applied load. In case of gradually applied load, there are no vibrations. So because the load is gradually applied, so this load is taken to gradually increases from 0 to maximum limit. 0 to maximum limit. So let us see gradually applied load. In this case, how the strain is varied. So let us consider a rod of length L and its magnitude P. That means the load in this case the load is P. The load P may be applied axially on a member of length L and uniform cross section area. In this case, delta L be the extension. Delta L be the extension. Let small p or sigma be the stress intensity. Small b or sigma be the stress intensity. So the graph would be in between load versus deflection. As the load increases, deflection also increases up to a proportional limit. Beyond the proportional limit, the material may fail. The material may fail. So what is meant by the strain energy? Strain energy is the energy absorbed or stored by a member when work is done on it. When work is done on it to deform it. So now calculate the work done by the external load. So how to calculate work done by the external load? The figure shows or this graph shows the area under the deflection curve. Area under the deflection curve represent the strain energy in this case. Strain energy in this case. Now calculate the strain energy in this case is equal to half into P. Here load P and deflection be the delta L. So now equating the strain energy stored by the member to the work done by the load. Work done by the load. So as you know that strain energy is the energy absorbed or stored by a member when work is done on it to deform it. Now you know that strain energy formula is sigma square into LA by 2E or P square into LA by 2E. Here sigma indicates the stress intensity or P indicate or sigma or P indicates the stress intensity. L indicates the length of the bar. A is the area of the cross section. E is the Young's modulus. Now half into P into delta L is equal to sigma square L into A by 2A. To cancel, delta L is equal to sigma square L into A, E into P. So now we know that sigma is equal to load by area. It is nothing but stress intensity. Sigma is equal to P by area. Substitute sigma value in this equation. So therefore P square in by A square into L into A, E by P. P cancel. Finally you get delta L is equal to PL by AE. PL by AE. So what is the formula for strain? Strain is equal to change in length by original length. Delta L by L. From this equation, delta L is equal to E into L. So stress is directly proportional to strain. Stress is equal to Young's modulus into strain. Therefore sigma by E is equal to E. So therefore delta L is equal to sigma by E into L. Sigma by E into L. Substitute delta L value in this equation. So sigma L by E is equal to P into L by AE. So therefore sigma is equal to P by A. So stress in this case here, sigma indicates the stress intensity, P is the load, A is equal to area of the cross section. So in this case stress is equal to P by A. P by A. This is for gradually applied load. Gradually applied load. Thank you.